Yeah, good morning. Welcome to the live session. We have discussed about the refraction of light at curved surfaces. In that lesson, especially the topic is discussed about here what is focal point or focus, then what is focal length of the lenses related to concave lens and related to the convex lens. Both we have discussed. Here, when a parallel beam of light rays incident on a double convex lens or maybe the double concave lens, after refraction, that light rays, in case of a convex lens, they can converge at a point. For a concave lens, they are appear to diverge from a point. So these converging point maybe or the diverging point is defined as focal point or the focus of the lens given as f1. Then the length measured between pole and the focus is given as a focal length. So up to there we discussed in the last classes. In today's class, I'll discuss with you about simply what happens if parallel beam of light rays incident on a convex lens. Right? What happens if a parallel beam of light rays incident on a simply they are said to be here behavior of a certain light rays. Behavior of a certain light rays when they are incident on a lens. It may be for a concave lens or maybe the convex lens. Both will discuss. So in the situation one, we are going to discuss about the light ray passing through a lens, but that light ray along the principal axis. Along the principal axis, it is for any lens. Along the principal axis for any lens it is. So here suppose we will take a double convex lens. So from this onwards, we are using symbols of the lenses, right? So just I will remind you what are the symbols. Here suppose if you join the that edges, what you'll get simply the shape you will get here double convex lens. So this is the symbol of a double convex lens. So here simply identify a point on the lens surface. So before that, I will take a horizontal line passing through that. So identifying that middle point on the symbol of the lens is given as pole. Then the line passing horizontally by joining the center of curvatures and the pole is given as principal axis. The line which is passing through the center of curvatures and the optic center of the lens is given as principal axis. Then identify their focal points, f1 and f2, exactly middle to the pole and centers, right? So they are given as here f1 and f2. They are given as f1 and f2. So these are required for us in any ray diagram for a double convex lens or maybe for the double concave lens. First of all, you have to draw their center of curvatures, focal points, principal axis and symbol of the lens, optic center. So everything as you see on the screen. After this, here the task is given for us along the principal axis. Along the principal axis. So here simply along the principal axis. So here the line joining the center and the pole is called principal axis. Then if you instant a light ray, that condition is given along the principal axis. So here I am taking a light ray that is along the principal axis. So blue color ray is given on the principal axis. Then where you cut the normal, the line joining the center to the boundary, right? So here that line you will get exactly along the principal axis. So where there that incident light ray, isolates normal, both are along the principal axis. So here, simply this case is considered the light ray is incident on the double convex lens normally. So when you incident a light ray normally on any surface, there is no deviation after the refraction. Actually, no refraction. It goes straight, does not bend. So we can trace the light ray after the refraction without any deviation, as you see here, green colored light ray. Green colored light ray. So this is given in your textbook as figure number 9A. Figure number 9A. Then what happens if you insert that light ray along the principal axis on a double concave lens? So now we'll go for a double concave lens. So symbolically, the double concave lens represented on the screen. Then same process, identifying its pole. Then identify their center of curvature size C1 and C2 here. After that, just join a line, right? What is center of curvatures and the pole? Join them with a line. So that line we can call it as here principal axis. After that, respectively identify their focal points. So left side F1, right side F2. So why they are actually opposite? So here we have the focal points. Then the light ray incident on a double concave lens. Light ray incident on a double concave lens, that is along the principal axis. So in this case also, we will consider that light ray incident normally on the double concave lens. Incident normally on a double concave lens. So when a light ray incident normally, there is no refraction. So light ray propagates without any deviation after refraction along the principal axis only. So after the refraction, the light ray remains along the principal axis. So we can generalize here, ray passing along the principal axis for any lens. For any lens, what happened? Here in both, we observed the light ray remained undeviation, no refraction. So the generalization we can give here that light ray remains undeviate. So this is the generalization here. If a light ray incident on a double concave lens or a double convex lens, after refraction, it remains undeviate. So that we have generalization from this ray diagrams. The next, situation number 2. What is the situation number 2 here? In the situation number 2, we will discuss if a light ray passing through center of any lens, right? Passing through center of any lens. So here, through the center of lens, sorry, actually it is not passing through the center of lens. Here, optic center of the lens. Pronunciation is different. So I said center. No, optic center of the lens. Ray passing through optic center of any lens. So in this case, what happens? So here, same process will follow, identifying the pole of the lens, then naming it as P. Next, identify their center of curvatures respectively as C2 and C1. Then next, joining the center of curvatures and the optic center. Okay, then give it as a principal axis, respectively their focal points. So here, what happens if a light ray passing through optic center of the lens? So light ray considered passing through. So here, remember one thing in this case, in this chapter, we are discussing about the lenses, especially negligible thickness, right? So here, in this case, there is no thickness to the lens, right? Negligible thickness. So in this case also, we will consider that refraction of the light ray when it passes through the optic center of the lens, not considered. There is no deviation. So in this case, the light ray passing through the optic center after refraction remains undeviate. So you can extend the light ray after refraction, just straight. So no deviation. So along the principal axis and through the optic center of the lens, in both the cases, the light ray remains undeviate. When a light ray incident on a double concave lens passing through the optic center, what happens? So here they are explained in the figure number 10A and 10B. So look at the double concave lens also here, identifying the pole. Then next, naming it as P, optic center. Next, identify their center of curvature size C1 and C2. Next, join them, name it as principal axis. After that, respectively, their focal points F1 and F2, their respective sides F1 and F2. Then, incident a light ray passing through optic center. Then what happens after refraction? In this case also, the light ray goes straight without any deviation. So what the generalization we can derive from this? In this case also, the light rays remains undeviate, is also undeviate. So here, a light ray incident on a double convex lens or double concave lens along the principal axis or through the optic center, then remains undeviate. So this is the generalization we can derive from the situation 1 and situation 2. So here situation 3, we'll go for situation 3. In this situation 3, we can consider the light ray traveling parallel to the principal axis, traveling parallel to the principal axis. So here, light ray traveling parallel to the principal axis. So we can draw lens symbol, double convex lens, identifying the pole, center of curvatures, then joining them called principal axis. So we have all the terms. Identify their focus F1. So why I'm taking focus F1 to the right side here? See here, from left to right we are considering. This is first surface. This is first surface. So here for first surface, we have its radius on right side. Radius on right side. So that's why I'm showing you right side. It's a focal point 1, F1. F2 automatically left side. So F2. Then incident a parallel light ray. So I already considered parallel beam of light ray. I'm considering a parallel beam of light ray. Suppose if you take only one ray, we will consider. So here suppose I'm showing you here only the one light ray. So here suppose what happens? This ray is parallel to the principal axis. This ray is parallel to the principal axis. What happens after the refraction? So here simply that light ray bends towards the normal. Bends towards the normal. So in this case, that light ray will be focused on the principal axis. On the principal axis. So here simply that light ray after the refraction passes through the focus. All the light rays after the refraction passes through the focus. So this is the generalization we can give. So in case of double concave lens, what happens? So that point F1 is given as focal point. Then next, here double concave lens. Center of curvatures C1 and C2. Then joining that center of curvatures passing through the pole is given as principal axis. Then what happens? After identification F1 and F2, what happens if a parallel beam of light ray incident on a double concave lens we are observing? So here in this case, light rays refracts. Already in the previous discussion, before defining that focal points, we observed what happens when the parallel beam of light ray incident. So I such that we are considering when a parallel beam of light ray incident on a double concave lens, they are going to refract. But here along the principal axis, that light ray remains undeviate. What about the other rays? They can refract, but they appear to diverge from the focus. They appear to diverge from the focus. So in the backward direction, you will get a common point at F1, that with the backward light rays. So that point we are defined as already focal point or the focus of the light rays. So in the backward light rays, so they can appear to meet at a common point F1. So that point is here, focus or focal point. Focus or focal point. So this is the situation number 3. This is the situation number 3. So what we generalized from the situation number 3, rays traveling parallel to the principal axis and incident on a double convex lens, they are converge at the focus. If it is incident on a double concave lens, they appear to diverge from the focus. So this is the generalization from the situation number 3. Then here we'll go for situation number 4. That is here simply what happens when light rays passing through focus. Light rays passing through focus. So in the previous case, we considered parallel to the principal axis. In that case, in double concave lens, they appear to diverge. In the double convex lens, they are going to be converge. Now, we are taking the converging light rays or diverging light rays, right? So, converging light rays or diverging light rays. So, here simply for double convex lens, we can consider diverging light rays. So, from where they can diverge? From the focus. So, here draw a lens, then symbolically they can here C2 and a C1. The next identify its a pole by drawing a line joining the center of curvature. Then the lens and principal axis, they can converge at a point that we will take it as here. It's a pole, optic center. So optic center is given. Identify it as pole or P. Then next here, draw its focal points as F1 and F2. So left side F2, right side F1. Then next here, simply we consider a situation rays passing through focus. Rays passing through focus. Suppose if I instant the light rays on the lens that which are diverging from the F2. So look at that. Look at that. So here one of the ray along the principal axis. Along the principal axis. That certain behavior of light ray we already know. We already know. What is that remains undeviate. Then what about the light rays? If parallel beam of light ray incident on a double convex lens, they appear to meet at a common point. Already they are at a common point, right? So after the refraction, they becomes parallel. So one of the ray passing along the principal axis remains undeviate, that is along the principal axis. Then these light rays already refracted at respective points from their respective point of incidence. So they are became parallel after the refraction here. They are became parallel after the refraction here. Then what happens in case of double concave lens? Double concave lens. So look at the double concave lens. Then identify the center of curvatures as C1 and C2. Then join them with a line called the principal axis. Then where they coincide, there you can identify a point and name it as optic center. The next respective focal points as F1 and F2. Next instant, the light rays which are seem to be meet at a common point, converging light rays now. In the previous case, that in the double convex lens, so we consider diverging light rays. Now converging light rays. Converging light rays are what? Before incident, they appear to meet at a common point. So all the light rays are going like this onto the lens. So they can meet at a common point. They appear to meet. but actually they won't appear as at a common point, right? So in this case, what happens? In this case, what happens? So we know one thing. What is the light ray which is along the principal axis remains undeviated. So here, after the refraction, one of the light ray goes along the straight principal axis. That is along the principal axis. So what that light ray is actually, here the light ray is along the principal axis, this one remains undeviated. Remains undeviated. Then what about the other? Here, simply, it is similar to the figure that 8A, B, C, D given in your textbook, but opposite, right? So here appear to meet at a point. They won't meet at a point because after the lens, they are going to refract. So after refraction, they won't meet at a common point. They becomes parallel here. So that light rays become parallel to the principal axis. So simply opposite. Figure number 8 ABCD and figure number 11 AB. Look at them respective to there. So simply ray passing through focus will take a path that parallel to the principal axis for any lens here. For any lens after refraction. So ray passing through focus will take a path parallel to principal axis after refraction. Will said to be refraction, there becomes parallel. So these are the situations. So these situations we can use in the ray diagrams to explain about the characteristics of the image obtained by the lenses, right? So in that we can use them. In that we can use them. So here now we'll go for another. That is here special situation. That is here special situation. So what is that special situation is here? Simply the special situation is nothing. What happens when a parallel beam of light ray falls on a convex lens or concave lens? Sir, already completed in the previous only. But here the special condition is parallel beam of light ray only, but I didn't mention as parallel to the principal axis. I'm not mentioning you. But here what I am specially mentioning here, that parallel beam of light ray only making angle with the principal axis. So when a light ray, parallel beam of light ray falls on a convex lens or maybe on the concave lens also, but making with the principal axis, what? Angle making with the principal axis. So in that case, what happening? In that case, what happening? That we are observing here. So what happens? What happens? That we have to look at. So in this case, how to deal? Just observe carefully. I'll use the same situations only. I'll use same situations, but something different logically, right? So simply I drawn a double convex lens symbolically. The next I'll identify their center of curvatures and naming them as C1 and C2 respectively. Then join with a line called principal axis. So identified the pole, then drawing its points. After drawing line also you can make this, no problem. Okay, that I will tell you later. So here all the points are recognized, then joining with a line called principal axis. So all the points lie on the principal axis only, remember. So C1, C2, F1, F2, then pole. All the points are lying on the principal axis. Don't get any confusion. Then what happens if a parallel beam of light ray incident on a double convex lens making angle with the principal axis? So now look at how to take that light rays. So here I'm taking the light rays parallel to each and every light ray, but not parallel to the principal axis, making angle here. So look at that angle made by that light rays, something theta, right? So here they are making angle with the principal axis. They are making angle with the principal axis. So then what to do? So here, is there any situation here suitable? Any situation? Does it meet? So it does not meet any situation. In the behavior of light rays, we discussed 1, 2, 3, 4. Does not meet. So what to do in this case? What to do in this case? So what to do? Simply, we can go for a situation. One of the situation is there. What is that? Simply, here, second situation is not there. What is that? Sorry, first situation is not there. First situation is not there. What is first situation? This first situation is along the principal axis. Is there it? No. Second situation, through pole. Yes, it is there. Then 3, parallel to the principal axis, not parallel. 4, passing through focus, not possible. So only one situation it is going to meet. Okay, this is enough for us to know what happens after the refraction. So now simply I am depending on situation number 2. Situation number 2. So what is situation number 2? Passing through optic center. Passing through optic center, pole. So in that, I know no deviation. Right? What I observed? No deviation. So simply we will go for that condition, no deviation. So what to do? This blue color ray, light ray given with blue color remains undeviated. So what to do is simple. Just place your scale as you see on the screen along the blue color light ray, that light ray passing through optic center. Then extend it, remains undeviated. Remains undeviated. Then what to do? Then what to do? Simple. Here we need to know simply principal axis. Why, sir? Why principal axis? Here, if we have principal axis, what we will go for situation number 3. All the light rays are parallel to the principal axis, means they converge at a common point called focus. So here, simply this blue color light ray we can imagine as imaginary principal axis. Imaginary principal axis. Right? So here, simply, then you can draw a perpendicular that which is passing through focus on the principal axis, where we can draw the perpendicular on the principal axis, but passes through focus, F1. So draw a perpendicular line through focus, F1. So place your scale as you see on the screen. Then what to do? Draw a dotted line through F1. So now observe the light ray which is passes through optic center coincides with the line drawn perpendicular through F1. Right? So that line we can call it as focal plane. The dotted line which is drawn perpendicular to the principal axis through F1 is called as focal plane. So here focal plane is nothing, a plane perpendicularly imagined to the focus. A plane perpendicularly imagined to the principal axis through focus or at focus. Right? So that is considered to the focal plane. Now identified a point that focal plane and the light ray after refraction which is remains undeviated as here imaginary focal point. Then joining all the light rays at that point. Joining all the light rays. So this point is called, look at that point here. This point is called imaginary focus. Imaginary focus. As F1 dash. So this point is F1 dash. Then Simple thing, just all the light rays before refraction, where they incident on a point lens, that points are connected directly with this imaginary focus as you see here. So this is the special situation. So why should I consider actually? Because we observe practically by incidenting the parallel beam of light ray at various angles. So that's why here I am giving you generalization. So look at that. What happens if a parallel beam of light ray incident on a double convex lens at various angles, right? So look at that figure now. So I can change the angle on the lens. So before refraction, they are parallel. Look at here. These light rays are parallel before refraction on the double convex lens. On the double convex lens. But they are always lying in a plane. So line drawn, see here. Right? So here simply look at that. See here, all the light rays are going to be converged at a point called as focal plane. Called as focal plane. So here this is called as focal plane. The line which is perpendicular to the principal axis called as focal plane. At any point, you can consider the point of converging light rays given on the focal plane is called imaginary focus. So this is actually we are considering in this special situation. What is special situation? Is simple. Parallel beam of light ray only, but making angle with the principal axis. At any angle, after the refraction, that all the light rays are converging. That converging point always lying on the focal plane. That you have to remember. This is practically observed. That's why it is given you generalization. So what happens? What happens if a light ray incident on the double concave lens by making something angle, right? So now we'll go for the special situation related to the double concave lens now. What happens when parallel rays of light falls on a double concave lens making angle with the principal axis? So we'll go for the same drawing. How to draw it? So I consider double concave lens symbol, then identifying their center of curvatures, next identifying the pole, giving as P, then identifying their respective focal points after drawing the principal axis. So principal axis is drawn by joining the pole and the center of curvatures. Next, here focal points as F1 and F2. Okay, given. Next, here our situation, parallel light rays making angle with the principal axis. So look at that. Parallel light rays are drawn. But one of the light rays, especially I am considering, if you focus, one is passing through the optic center. I didn't miss that light ray. Parallel only, but don't miss a light ray. One is passes through optic center. So I never miss that. So now what happens? As we learned in the situation number 2, when a light ray passes through optic center, does not refract, do not deviate, so go straight. So simple, that light ray we can use, place your scale as you see on the screen, then extend it. Then what to do? Then go for focus. Go for the focus. So where is focus? That imaginary plane assumed perpendicular to the principal axis through the focus is called focal plane, diverging point, right? So that we can consider. So draw a perpendicular through F1 where they can coincide, that remains undeviate, that light ray. Maybe it is actual light ray or backward light ray. So that point we can call as, right, focal plane, and the point coincides with the undeviate light ray is called imaginary focus. So I got a imaginary focus here. I got a imaginary focus here. So this point is now considered to be focus. Now see here, pole and focus is connected with a line called principal axis. So this remains undeviate light ray is considered now as imaginary principal axis. So we have imaginary principal axis. What about that light rays? Appear to parallel to the principal axis. Imaginary principal axis. Appear parallel to the imaginary principal axis. We know that lens is diverging lens. So these light rays appear to diverge from the focus. Appear to diverge from the focus. So now we can draw the refracted light rays by connecting the point of incidence. So this is point of incidence and imaginary focus. So we are considering that are connected like this. So we will go for that situation here. So now look at them. That points are joined here. All the incident points joined. Then what happens? They can be extended after the refraction. They seem to be emanate from the focus. So using that logic, situation number 3, parallel to the principal axis. So according to that, we can extend that light rays in the same direction. Seem to be emanate from the focus. So this is special situation for the double concave lens. So why you consider? Because practically we assume, as observed, not assume. Practically we have observed. So look at that practical on the screen. So here simply the rays converge at a point or appear to diverge from a point lying on the focal plane from the both figure 12A and 12B. We are giving generalization. So look at that practical animation. Parallel beam of light ray focused on the double concave lens. But what happening here? See. What happening here? See. Always that chaining. Here diverging. After the refraction, they are diverging. But always they seem to meet at a common point everywhere. See here, that point always lying on the plane called focal plane. Right? So principal focus, then remaining any point you can consider on the focal plane is called a imaginary focus. Principal focus is F1, but remaining any point you can consider. So this point we consider in the diagram, so that we can call it as imaginary focus and giving it as F1 dash. So they appear to diverge. So this practically observed. That's why we are given generalized. The rays converge at a point or appear to diverge from a point lying on the focal plane that respective to the lenses. In case of convex lens, on the focal plane, always that parallel beam of light ray, it may be with any angle, they converge at a point. Suppose if it is a concave lens, right, parallel beam of light ray, making any angle with the principal axis, they diverge from the focal plane point. Okay, so this is special situation. So special situation is completed. After this, we will go for another. That is here simply we are going to learn about rules to draw the ray diagrams. Rules to draw the ray diagrams. Okay, actually we have a practical lab activity, right? But I am not explaining the lab activity directly because we are learned about the situations. Okay, we have to go for that. But before that only, we are drawing the ray diagrams and we are verifying that ray diagrams with the lab activity, practical. So experimentally, we can verify these ray diagrams, right? So for that, I am taking a topic, rules to draw the ray diagrams for image formation by the lenses. So image formation by the two rays, as we learned in the first chapter, reflection of light. In the reflection, we consider two light rays. So in this also, we will consider two light rays. that we learned from the situations. Situation 1, 2, 3, 4. So for that, just I am considering a double convex lens here. So I can draw a double convex lens along with the principal axis. So first of all, I drawn a line horizontally on the paper, right? So horizontal line. So always for drawing the ray diagrams, use landscape mode paper. So use your paper or notebook horizontally, landscape mode. Then draw a line, principal axis. That is what? Principal axis. So then select its midpoint to place a lens symbolically, midpoint of the line. So that is what here simply lens. Your double convex lens is given. Okay, then next here, identify that converging point of this line and the lens is optic center, P, pole. Then respectively their center of curvatures and the focal points. So here equal distances you have to maintain to identify that points on the principal axis. Left side as well as right side, equal distances. So here this gap, same, whatever it may be, on the possibility, depending on the paper length, you can take. Okay, so that gaps equally you have to maintain. Then C1, C2, F1, F2, respective to the lens. So then here we are representing object with an arrow at any place except infinity, always above the principal axis. So representing object with an upward arrow above the principal axis. So as you see on the screen. So this is what? Object. This is what? Object. So here object represented above the principal axis always with upward arrow. Then remember the rules, right? Always the object is represented above the principal axis with an upward arrow. Then here considering the situations, behavior of certain light rays discussed. In that situation 1, 2, 3, 4 we discussed. So any two situations are required here, right? That which are suitable in this diagrams. So what they are here, always the two light rays selected from the same point. Always the two light rays are selected from the same point. So that same point is what? Top of the object. Top of the object. So light rays are always selected from the top of the object only. Two situations. So which are possible here? The situations are parallel to the principal axis, along the principal axis, through the optic center, and passing through the focus. So that two light rays are fixed here. Always fixed light rays we will consider. What they are here? Simply they are here. One is parallel and the other is passing through pole. Fixed. So situation number 3, situation number 3 and situation number 2. These two only will consider. Passing through optic center and passing through, parallel to principal axis. So two light rays we are considering. Two light rays we are considering from the top of the object. One is parallel to the principal axis from the top. So one is parallel to the principal axis as you see. Then next one is passing through optic center. Then second ray. So always fixed for any lens. So first light ray and second light ray. Right? One is parallel to principal axis and the other is passing through optic center. So we know when a light ray passes through optic center, remains undeviated. So you can extend the second light ray first without any deviation straight. The next rule is first light ray parallel to the principal axis. In case of double convex lens, we know that converge and passes through focus. So you can draw a line light to the focus. Then look at that. Do that light rays meet at a common point? No. That light rays are going to meet at a common point? No. Then what to do? We can extend that light ray which is passing through focus to get a converging point. So I obtained that converging point is here given with the green color point. So at this place you obtained a converging point of refracted light rays. Converging point of refracted light rays. If you won't obtain converging point, right, then what to do? They may be diverged. So extend them in the backward direction. In the backward direction. So in the backward direction, maybe they will give you a common point. So you will get a diverging point. So whatever it may be, after refraction, obtaining a converging point or obtaining a diverging point, that converging point or diverging point given by the refracted light rays is called as image point, what you consider. So here top of the object is considered. Top of the object is considered. That converging point of the refracted light rays or diverging point of the refracted light rays will give you top of the image. So these are the rules to draw the ray diagrams. So one more rule is there. After obtaining this point, you have to draw a perpendicular onto the principal axis from the converging point or diverging point. So in this case, I obtained converging point. From there, I can draw a perpendicular onto the principal axis and directing the arrow towards the point from the principal axis. So image is obtained downward principal axis facing downside. Below the principal axis facing downside. So that arrow representing direction always towards that converging point or diverging point. Right? So where you obtain. So these are the rules. So here simply we can go for the characteristics. Right? So these are the rules we are obtained from the diagram. So these are the rules. Then logical rules I will give you. I'll give you logical rules. So what are the logical rules here? What are that logical rules? So for that logical rules, I'll give you simple. Suppose this is a white color screen. Imagine eyes simply a paper. So how it is? As landscape mode. Length is more, width is less, height or width. So landscape mode. So use always your notebook or the paper on landscape mode. Then use your long scale, draw a line within the margins, page borders. So within the borders, you can use the scale as you see here. Then draw a horizontal line. So start from one end and go to another end of the scale. Then the line is drawn. Then, so this is you are considering as principal axis. So I got a principal axis. Then what to do? Use this as your principal axis. Then place your lens. Right? So at the midpoint, draw a lens. Suppose here I am drawing convex lens. Okay. Then name it as pole. Pole is named. Then what to do? So here simple. The logic is giving you always that points located from the pole may be pole to the focus or focus to center or pole to the focus. Sorry, pole to the center. Logically, they are at equal distances. I will consider. So look at the scale is placed. So pole to the center, I'm using 8 centimeters. Right? So that point at 4 centimeters, one pointer, and at 8 centimeters, one more pointer. So what I'm giving logically here, pole to the focus 4 centimeters and focus to the center also 4 centimeters. That means here pole to the center is 8 centimeters. So equal width, equal gap you are maintaining. Then right side also same thing, 8 centimeters. So here 0 to 4, 1 point, and 4 to 8, one more point. So 2 points obtained. Then remove your scale, then name them respectively C1, C2, F1, F2. So namings are given here respective to the lens. So for the concave lens also will follow the same logics. For the concave lens also we'll follow the same logics. So concave lens symbol we can draw, and respectively C1, F1 are left side, C2, F2 are right side for concave lens, depending on the surfaces and the spherical shape assuming, right? Then what rule? So always the object is parallel to the, above the principal axis with an upward arrow. But here, logically, I am following the height of the object exactly equal to the width of the scale. Why? Because to draw the parallel light ray easily, right? So width of the scale is used for the object height. For any position, always take the object height above the principal axis equal to the width. Height of the object is equal to the width of the scale above the principal axis. So use to put the scale as you see on the screen. Then draw the object at any position. Then next here we'll go for light rays. So what are the light rays suggested here? Only two light rays from the same point, top of the object. One is parallel to the principal axis and the second one passing through optic center. So at a time, after drawing the object, draw a parallel light ray from the top of the object. So drawing completed. Then remove your scale. Next, second ray passing through optic center. So put your scale, join the top of the object and optic center as you see here. Then just draw a line as a ray. Then what happens we know? Remains undeviate. So here simply I have given logically. These are the logical rules we are following to draw that. Then complete the ray diagram, whatever it may be. So here simply we can extend or join this first light ray parallel to the principal axis. It passes through optic center. So draw that. Extend it for a distance. Then next one passes through optic center, remains undeviate. So joining. So already I am obtaining a point, common point. So that common point is what for us? Image point, top of the image. So from the top, where is the bottom? That is on the principal axis only. So that's why you are drawing a perpendicular onto the principal axis from the converging point obtained from the refracted light rays. So that is image. So object to image are obtained. So these are the logical rules you are following to draw the ray diagrams. Draw the ray diagrams. So here simply we will go for the possible positions for the object, where you are able to place the object at various possible positions on the principal axis, right? So what they are here, suppose if you take a double convex lens, I mentioned the logical rules. So lens is there. Then is there any noun places to you? Yes, we have noun places. What they are here? Focal points as well as their center of curvatures on the principal axis. Any side. We know 2 points, left side or right side. What they are? One is focus and center of curvature. So logically, I know left side 2 points. They are here focus and center of curvatures. Focus and center of curvature. Suppose if I place object at very far distance from the lens, at very far from center of curvature. So if an object is placed at very far beyond the center of curvature, that we will consider as here infinity position. So object is said to be at infinity. For that, what the object will be represented as. So here actually we won't show the object. We will not show the object. So no representation of object for the object beyond the center of curvature, very far, considered as infinity. So one of the position is given as object is located at infinity. The next position beyond the center of curvature, but somewhat near. Outside center, but nearer. So somewhat here we can consider that position is beyond C. So here very far infinity, outside near only, measurable distance, that we can consider simply beyond the center, that is outside the C2. So in this case, we will represent the object with an upward arrow. So look at the arrow drawn above the principal axis outside the center of curvature C2. Then it is called as beyond C2. Object is placed beyond C2. So object placed on the principal axis outside center of curvature is given as beyond C2. The position is said to be beyond C2. So this is the position, second position. The next, exactly on the center of curvature C2. So that position we can call it as at C2 or on the center. So object representation exactly at C2 with upward arrow given as C2. Sorry, C1 written, C2. Next here, simply inside the center. Outside the center, beyond, exactly at center, on the center of curvature. Now we are moving inside. So we have location eyes here, C2 and F2. In the middle, we can take that. So we can give that inside the center of curvature, outside the focus, between focus and the center. So we can represent as between F2 and C2. Then object representation with upward arrow at any place between, at any place between. So object placing above the principal axis between F1 and C1, as you see that blue color light ray. Then next one, moving exactly to the focus. So we can represent as that on the focal point at F2. So object represented with upward arrow. Then object placing above the principal axis on F2. On F2. Next here, inside the focus. So we have two locations. One is F2 and the other is P. So object brought between, right? So now we can say that position possible lies between pole and the focus. So between P and F2. So object is placed between principal axis and the focus F2. So these are possible positions. So after this, we have a topic that is ray diagrams. So ray diagrams we will discuss in the next class. I think it is understand to you. If you like my classes, just share it with your friends. Also give your valuable comments on the comment section on YouTube. Thank you for joining in the live session. I will give